My name is Mihai Bibrida, and my collaborators are Valentin Slepukin and Professor Alexander Levine. And my presentation today will be on dynamical phase separation on rhythmogenic neuronal networks. We investigate a neuronal microcircuit called the pre-Botzinger complex, which generates the mammalian breathing rhythm. The circuit is composed of on the order of 10 to the 3 neurons, and it can be modeled computationally by a directed graph. And in this graph, the vertices represent neurons and the edges represent connectivity between two neurons. We define a probability parameter p, which is the probability of an edge existing between two vertices in the graph, and we populate an adjacency matrix according to an Erdos-Renier model using this probability parameter. By convention, as I said, the graph is directed, so if neuron A connects to neuron B, it's not necessary that neuron B also synapses into neuron A, so the matrix is not symmetric. And the diagonal elements are 0, which is to say that a neuron cannot synapse into itself and support its own firing. Now, there are 3 distinct mathematical phases of the network. The first and most interesting phase, the dynamical phase, is the stably oscillating phase, where neurons oscillate between a firing and a non-firing state. Biologically, this is equivalent to a steady breathing rhythm. There are also 2 flavors of fixed point phases where the neurons do not oscillate between firing and non-firing, and this is an example of one of those fixed points. We distinguish between a fixed point as either a high activity fixed point or a quiescent fixed point, depending on the average voltage output of the network with respect to the threshold voltage activation for the neuron. So this would be an example of a high activity fixed point where most of the neurons remain in a firing state. And we also have a state where the neurons all turn on and then they turn off and remain off for the rest of the simulation. And this would be an example of a quiescent fixed point. So we center our investigation of these networks using a Feldman-Del Negro firing model, which is described by a system of 2n coupled differential equations, where n is the number of neurons in the network. And so there are these 2 time-dependent voltage and calcium concentration parameters. So the voltage change of neuron I is determined by the deviation of the neuron's voltage from its equilibrium voltage, and the sum of input firing rates from adjacent neurons, which is captured by this MIJ adjacency matrix parameter, and then this firing rate, R of Vj is this firing rate as a function of the voltage at neuron J. And this sum of input firing rates is scaled by this sigmoidal voltage increment function, which is dependent on the neuron's calcium concentration. Likewise, we have a similar determination for the calcium concentration of neuron I. However, this time these input firing rates are scaled by this constant calcium concentration parameter. So at the neuronal level, the voltage increment and firing rate functions are described by sigmoids with a defined sharpness parameter, GV and GC. So these are these sharpness parameters. And in our investigation, we actually manipulate these parameters, even though it is aphysical. We manipulate these parameters to understand how changes at the neuronal level affect network dynamics. And so what that steepness parameter does is basically we have these smooth sigmoids in orange, which are the physiologically relevant regime. And then we can mathematically tune the steepness parameter to look more like this step function, to have this step function-like behavior. So interestingly enough, we observe this symmetry breaking phenomenon in all-to-all coupled networks when we adjust this steepness parameter. We first begin by observing this n delta v phase diagram, which appears to have a shape consistent with prior experiment and demonstrates 3 distinct phases for the network's dynamics. So the way to interpret this phase diagram is we basically fix a value of delta v, and we start with a toy network with all of its neurons intact, and then we slowly remove neurons from the network until we observe a phase transition. So this blue regime is the quiescent fixed point regime, this purple is the stably oscillating phase, and dark green is the high activity fixed point phase. We also observe these 2 yellow and light green phases, which we call below and above threshold oscillations. These phases do not have a physiological effect, and while they are oscillations, they are different from stable oscillations because they do not cross the voltage activation or calcium concentration activation functions. And so biologically, this is basically a quiescent fixed point, and this is a high activity fixed point still, even though mathematically, technically, they are oscillations. On the right here, we study analytical solutions to the system of equations above, which is a simplified form of the earlier equations, since we are considering an all-to-all coupled network. And we observe that for smooth sigmoids, there exists precisely one stable solution to the network's dynamics. And when we change the smoothness of the sigmoid to we transition that to the step function limit, we observe what's called pitchfork bifurcation, where our one stable point becomes three distinct fixed points. And this is a phenomenon called phase separation, where some of the neurons are in an on state, they're firing, and others are turned off. And so the initial permutation symmetry of the neurons is effectively broken now that we have these three stable solutions. And so this is a diagram showing how that happens exactly. So we have, in this case, one neuron remains on while the rest are off by the end of the simulation. Now you'll notice that there's a combinatoric relation of the number of neurons that can actually be on or off. In this case, one neuron can be on and the rest are off, and the specific ordering of those neurons can be shuffled around. So when we have our fully connected network, we have this combinatoric relation where we have n as the number of neurons in the network, and NL as the number in low activity phase, and NH as the number firing. So we have this combinatoric relation. And so we ask the question of how many fixed points are possible as we transition from an all-to-all coupled network to a more sparsely connected network. And we study that by we begin with an all-to-all coupled network, and we simply remove edges one by one from the network, which has the effect of lowering the connection probability parameter P that I mentioned earlier. As we do this, we randomly sample the steady state voltage of each neuron in the network for a large number of identical networks, and we enumerate the number of unique fixed points that we observe. The number of unique fixed points for a given set of parameters in sparse networks turns out to rapidly decrease as a function of the connectivity parameter P, starting at P equals 1 with this combinatoric relation I mentioned earlier, and rapidly decreasing at around P is slightly greater than 0.9 to singular fixed point values. So this is kind of where we begin discussing the effects of network topology on the dynamical phases. And so we study a particular limit of the model, and we need to introduce a concept of K-cores, as this is the context in which these networks were discussed previously. So we need what is a K-core exactly? A K-core is a maximally connected subgraph of G whose vertices are connected to at least K other vertices within that subgraph. So I have here a model network where I just basically generated random connections here, and we're going to try to find the K equals 1 core of the graph. So trivially, all the neurons in the graph belong to the K equals 1 core. As we go to the K equals 2 core, we need to apply a K-core finding algorithm, which involves basically visiting each vertex in the graph recursively and removing vertices with less than K incoming edges. So in this case, we need to remove neuron 3, and we're left with the 2 core of our graph is just the graph with that neuron removed. As we go to the 3 core, we apply the algorithm again, so we need to remove neurons 0, 1, and 2. And then we apply the algorithm recursively, and we need to remove neurons 4, 5, and 6, and with them removed, neuron 7 also has to get removed because it has no neighbors. And so we see that our graph basically has a 1 core and a 2 core, however there is no 3 core. So we investigate the effect of network topology on phase separation by effectively binarizing our model of neuronal firing. We do this by applying the following constraints onto our system. So we're basically looking at a step activation function, and this ensures that a neuron is either firing or not as a function of its input voltages. And we focus on steady state solutions of the system of equations by identifying a lower bound on the number of firing neurons in the network, which are required to support a high activity fixed point. we observe that transitions from the high activity to the quiescent phase are exactly determined by the removal of particular k-valued k-cores from the network. And specifically, if we know at which neuron count a k-core vanishes, and the delta v parameter, this transition here can be predicted and computed exactly. And so the interesting realization that we get from this phase diagram is that basically the neurons that are firing in the network are the ones belonging to a particular k-core. When that k-core is removed, which is signified by these black lines here, when that k-core is removed, we see that the phase transitions from this high activity fixed point to this quiescent fixed point where none of the neurons are firing anymore. So the k-cores exactly determine the steps along this phase boundary. So prior investigations observed a similar dependence, although in a much more limited sense, along the stably oscillating to the high activity fixed point phase boundary. They observed basically a partial k-core dependence on the shape of this boundary. They observed these steps that corresponded closely to k-cores in some cases. And we confirmed those results. We confirmed that k-cores do partially determine transitions from the stably oscillating to quiescent phase on larger, or to the stably oscillating to a high activity fixed point phase on larger sparse networks. And this is consistent with prior analyses. So we confirmed that the disappearance of high k-valued k-cores influences the stability of the stably oscillating phase, and k-core transitions are present on these upper lips of these overhangs. Now, another result that previous investigations had, or another prediction, was that this phase boundary was actually monotonic, and that they didn't actually predict that there were these lips here. And we showed that there are actually these overhangs where, with the removal of neurons from the network, the stably oscillating phase can actually be recovered once it's lost. So previously it was thought that as you kill neurons from the network and the stable oscillations disappear, the only way to recover the stable oscillations would be to increase the neurons in the network or to adjust this delta V parameter. We show that in certain regimes of the parameter space, it is actually possible with the removal of neurons to both lose the stable oscillations and then to regain them again. So what this basically leads us to believe is that some neurons may have an overall inhibitory effect on the network, and their removal may actually stimulate oscillations. And this reentrant behavior is a new discovery, and this in our preprint of the paper we basically suggest experiments to test this fundamental aspect of the model. So that concludes my presentation. However, when I presented this earlier, there were three interesting questions that I wanted to share now. The first question was, are the phase diagrams for one single instance of a network? The phase diagrams that I've shown are all for one particular instance of a network at one particular probability parameter for defining the connection probability. And so the actual shape might change for different probability parameters, or even for different networks created with that same probability parameter. So that's a good question. Do all networks have reentrant behavior? Not all networks do have this reentrant behavior, particularly if certain parameters of the network are changed. And so we observe in some cases that we do see this reentrant behavior for particular delta V values. However, this is not present on all networks. But previously it wasn't observed in any networks, so we show that they do exist in some networks. Is this connected? In what ways is this connected to experiment? Well, all of the parameters for the simulations are derived from experimental values, which are measured in rat brains, and we work closely with an experimental group at UCLA that actually goes and develops the electrodes to investigate this particular complex in rat brains. Any further questions or citations can perhaps be answered in at this ArXiv link. And thank you very much for listening to my presentation.